All right, let's jump right in. Welcome to this explainer. Today, we're taking a geometric puzzle, something that sounds like purely abstract math, and turning it into a literal geographic adventure. We're going to track down the exact perfect mathematical center of a colossal shape drawn straight onto the Earth's surface. If you're the kind of person who geeks out over seeing pure math map perfectly onto our physical world, well, you are in exactly the right place.
So here's the massive puzzle we're tackling today. Where exactly is the center of a giant triangle that connects the North Pole to the equator? I want you to just picture that for a second. Try to visualize it on a globe. We aren't talking about some tiny shape you sketch on a piece of graph paper. We're talking thousands and thousands of miles, stretching across oceans and continents. Where does the absolute mathematically flawless center of all that space actually lie?
To start, we've got our canvas, a totally blank world map. Right now, it's just your standard continents, oceans, and those familiar grid lines of latitude and longitude. But this is the setting for our mystery. As we start plotting our points, try to keep the sheer massive scale of this space in mind.
Okay, let's actually draw this thing. We start way down at the equator. We draw a line from the prime meridian, that's exactly 0 degrees longitude, straight over to 90 degrees east. Then, from both of those bottom corners, we trace lines all the way up until they converge right at the North Pole. What we've got now is a spherical right triangle, and because we're drawing this on a sphere, it is perfectly symmetrical. Every single side is exactly 90 degrees long, and every single corner is a perfect 90-degree angle. I mean, this shape covers a staggering chunk of Europe, Africa, and Asia.
Now check out the intersecting lines cutting across our triangle. We are looking for the exact center point. If you were to draw a line from each of our three corners straight across to the opposite side, that exact intersection right there, that's our perfect point of balance. So, quick challenge for you. If you were standing exactly in the middle of this vast space, perfectly balanced between the North Pole and the equator, where on Earth do you think you'd actually be standing?
Let's figure it out. Section 1. Translating to 3D space. Moving from a 2D map to a 3D unit sphere.
When we look at the coordinates, it's actually kind of amazing how elegantly these geographic locations translate into basic 3D axes. You know, just simple x, y, and z coordinates, if we treat the Earth as a sphere with a radius of 1. Vertex A is right there at the equator and the prime meridian, so it shoots perfectly along the x-axis, giving us 1, 0, 0. Vertex B is on the equator too, but in 90 degrees east, which means it points purely along the y-axis, giving us 0, 1, 0. And then vertex C is sitting pretty right on top of the world at the North Pole, so that's a straight 1 on the z-axis, 0, 0, 1. It is beautifully, beautifully neat.
So here's the crucial takeaway. Because our giant triangle is perfectly symmetrical, again, 90 degrees on every side, 90 degrees at every angle, its exact center has to be a point of absolute, undeniable balance. No single axis can pull any harder than the others. That means right in the middle, the coordinate values for x, y, and z must be completely identical.
Which brings us to Section 2, the coordinates of perfect balance, calculating that exact center point. To find it, we use a concept called vector normalization. Now, please don't let the mathematical jargon scare you off, because the actual idea is incredibly straightforward. It literally just means we're finding that balanced center by adding our three corner coordinates together. That gives us 1, 1, 1. But here's the catch. A point at 1, 1, 1 would be hovering deep in outer space above the Earth. So we have to normalize it. We have to adjust it so it sits exactly flush on the curved surface of our sphere. To do that mathematically, we divide by the square root of 3. So at our perfect geometric center on the Earth's surface, the x, y, and z axes all equal exactly 1 over the square root of 3.
Let's bring this math back down to Earth, literally. The immediate geographic payoff here is that because our x and y values are identical, we instantly know our longitude. Think about it. When the geometric pole between the prime meridian and the 90-degree east mark is perfectly equal, that represents exactly a 45-degree angle. So without even breaking a sweat, we already know our center point's longitude is exactly 45 degrees east. We're halfway there.
But what about the latitude? Just how far north are we? Well, if we take the inverse sign of our z-axis value, that 1 over the square root of 3 we just worked out, we get our exact, highly specific latitude. Boom! 35.2644 degrees north. That is the aha moment right there. The absolute mathematical center of this massive, continent-spanning shape sits perfectly at 35.2644 degrees north and 45 degrees east.
All right, Section 3, the real location on the map. Grounding this abstract math in physical reality.
When we drop a pin directly on those mathematically perfect coordinates, it lands us smack in the middle of the rugged Zagros Mountains, specifically right on the border between the Kurdistan region of northeastern Iraq and western Iran. I mean, it is just wild how this purely abstract, perfectly clean geometry calculation drops us onto this very specific, rocky, physical mountain ridge in the Middle East. It's where math literally meets reality.
And just to give you a bit of geographical context here, if you were actually hiking out to this mathematical center point, you wouldn't be completely out in the middle of nowhere. About 55 kilometers to the west-northwest is the major cultural and educational hub of Sulaymaniyah in Iraq, and roughly 110 kilometers to the southeast is the historic industrial city of Kermanshah in Iran.
Now, for a really fun part, Section 4, a hidden geometric twist. Why our intuition about spheres is often totally wrong.
Take a look at the stark contrast between what our brains assume and what the math actually proves. If you ask practically anyone to guess the distance from the corner of a 90-degree shape to its dead center, human intuition screams that it should just be half, right? Exactly 45 degrees. But we're on a sphere, not a flat piece of paper. The mind-bending mathematical reality is that the true distance angle from any of our three corners to our center point is 54.7356 degrees. It is significantly further than a flat 45 degrees, and that's entirely because of the bulging curvature of the Earth.
And check out this elegant little equation, because it perfectly captures the sheer beauty of spherical geometry. If we take our center's latitude, which we found was roughly 35.26 degrees, and we add that true distance angle from the pole to the center, about 54.73 degrees, they add up perfectly to exactly 90 degrees. They completely complement each other. It proves that these ultra-specific, seemingly random decimal numbers, they aren't random at all. They are the totally inevitable natural result of perfect three-dimensional symmetry.
Which really brings us to a final, pretty profound thought. If our basic intuition expects flat, simple 45-degree answers, but the real world is operating on the complex, curving math of spheres, what other profound geographic mysteries are hiding in plain sight out there? The next time you spin a globe, just remember that the distances, the angles, and the centers aren't always exactly where your brain assumes they are. Thanks so much for joining me on this explainer. I really hope it sparked some curiosity for you. Keep exploring,